What I want to do in this video is think a little bit about what happens to some type of projectile, maybe a ball or a rock, if I were to throw it up, straight up into the air. So to do that, and what I want to do is I want to plot its distance relative to time. So there's a few things that I'm going to tell you about my throwing of the rock in the air. We'll have an initial velocity. I'll have an initial velocity of 19.6 meters per second. And I picked this initial velocity because it'll make the math a little bit easier. And we also know the acceleration near the surface of the Earth. We know that the force of gravity near the surface of the Earth is the mass of that object times, let me write this down. The force of gravity on an object near the surface of the Earth is going to be the mass of the object times little g, times gravity on Earth. This is 9.8 meters per second squared. Now, if you want the acceleration on Earth, you just divide force divided by mass, right? Because we have force is equal to mass times acceleration. If you want acceleration, divide both sides by mass. So you get force over mass. So let's just divide this by mass. Or let me divide both sides of this by mass. If you divide both sides of this by mass, on the left-hand side, you get acceleration. And on the right-hand side, right over here, you get the same quantity g. And the whole reason why I did this is when we look at the little g, it really comes from the universal law of gravitation. And you can really view it as as measuring the field strength, the gravitational field strength near the surface of the Earth. And then that helps us figure out, when you multiply it by mass, the force. Then you'll use F equals ma, Newton's second law, to come up with g again, which is actually the acceleration. And it's accelerating you towards the center of the Earth. The other thing I want to make clear, and you might have already thought about this, is when you talk about gravity, the force of gravity, generally you're saying, look, the force of gravity is equal to big G, which is different than the little g, times the product of the masses of the two things, times the square of the distance between the two objects. And so you might be saying, wait, clearly the force of gravity is dependent on the distance. And so if I were to throw something up into the air, won't the distance change? And you would be right. That is technically right. But the reality is that when you throw something up in the air, that change in distance is so small relative to the distance between that object and the center of the Earth, that to make the math simple, when we're at or near the surface of the Earth, including in our atmosphere, we can assume it is constant. We can assume it is constant. Remember, that little g right over there is really all of these terms combined. If we assume that mass 1 is the Earth, or mass of the Earth, and r right here is the distance, really the radius of the Earth, from the surface of the Earth to the center of Earth. Radius of Earth. So you'd be correct in thinking that it actually changes a little bit. The force of gravity changes a little bit. But for the sake of throwing things up in our atmosphere and all of that, we can assume that it is constant. And if you were to calculate it, it is 9.8 meters per second squared. And I've rounded here to the nearest tenth. And I want to be clear, these are vector quantities. And in this, when we start throwing stuff up in the air, the convention is that up, if something is moving up, we'll give it a positive value. And if something is moving down, we give it a negative value. Well, gravity would be, for an object that's in free fall, gravity would be accelerating it downwards. Or the force of gravity is downwards. So little g right over here, if we want to give its direction, is negative 9.8 meters per second squared. So we have the acceleration due to gravity. So the acceleration due to gravity is going to be negative 9.8 meters per second squared. And I want to plot distance relative to time. So let's think about how we can set up a formula, how we can derive a formula that if we input time as a dependent variable, we can get distance. And we can assume these values right over here. Well, we know, or even more important, I want to plot displacement versus time, because that'll actually be more interesting in this problem. So we know that displacement is the same thing as average velocity times change in time. So right now we have something in terms of time, distance, and average velocity, but not in terms of initial velocity and acceleration right over here. But we know that average velocity is the same thing as initial velocity plus final velocity over 2 if we assume constant acceleration. So we can do this assuming constant acceleration. And once again, when we're dealing not too far from the surface of the Earth, we can make that assumption, assuming we have a constant acceleration. But this right here, once again, we don't have what our final velocity is, so we need to think about this a little bit more. But we can express our final velocity in terms of our initial velocity in time. So this expression right here, so we're just dealing with this part of the average velocity. So we can rewrite this expression as the initial velocity plus something over 2. And what is final velocity? Well, the final velocity, I'll do it in that same yellow color. The final velocity is going to be your initial velocity plus your acceleration times change in time. Right? If you're starting at 10 meters per second and you accelerate at 1 meters per second squared, then after a second you'll be going 1 meter per second faster than that. So this right here is your final velocity. Let me make sure that these are all vector quantities. So all of these things over here are vector quantities. I sometimes might forget that. Forgive me. Hopefully by now it's pretty ingrained in you that these are all vector quantities, that the direction matters. And let's see how we can simplify this. Well, these two terms, and remember, we're just dealing with this average velocity term right over here. These two, if you combine them, become 2vi, 2 times my initial velocity, and then divided by this 2, plus all of this business divided by this 2, plus my acceleration times change in time divided by 2. So all of this was another way to write average velocity. And the whole reason why I did this is because we don't have final velocity here, but we have acceleration, and we're going to use change in time as our independent variable. And so we also have to still multiply this by this green change in time right over here. By this green change in time. And all of this was what displacement is going to be. This is displacement. And let's see, we can multiply the change in time times all of this business. And actually, these 2's cancel out. And we get, I'll continue it over here so I can use all of the real estate. We get that displacement is equal to initial velocity times change in time times change in, I'm doing that same color, times change in time. And a lot of times in a lot of physics books or traditional physics classes, they'll just write time there, but it's really change in time. And it's not super wrong if there's just a t here, but change in time is a little bit more accurate. And then plus you have 1/2, that's the same thing as dividing by 2, plus 1/2 times the acceleration times we have a delta t times delta t. Change in time times change in time. This triangle just means change in. So change in time times change in time is just change in time squared. Change in time squared. And in some classes, you will sometimes see this written as, maybe d is equal to vi times t plus 1/2 at squared. Same exact thing. They're just using d as the variable for displacement, and they're using t instead of delta t. These are the same things. But the one thing I want you to realize in this video is that this is a very straightforward thing to derive. You really, maybe if you're under time pressure, you might want to just make sure that just be able to whip this out. But the important thing, so that you remember how to do this when you're 30 years old or 40 years old or 50 years old, or when you're an engineer, you're trying to send a rocket into space and you don't have a physics book to look up, is it just comes from the simple displacement is equal to average velocity times change in time, and we assume constant acceleration, and then you can kind of just derive the rest of this. Now I'm going to leave you there in this video. We're going to leave off. Let me erase this part right over here. I'm going to leave it right over here. And in the next video, we're going to use this formula we just derived. We're going to use this to actually plot the displacement versus time, because that's interesting. And then we're going to be thinking about what happens to the velocity and the acceleration as we move further and further ahead in time.